Good morning, good morning, good morning, good morning. What about all of you celebrated Deepavali? Yeah? Yes? So how you celebrate Deepavali? Yeah? All of you? No reply? See, whether I am audible or not?
Yes, sir, you are audible.
Audible. What about Deepavali? Yeah, you are celebrating Deepavali. I think no one can express how you
Sir, it
celebrate.
was so good that we can't express.
Okay. I think this time compared to last year, this time the crackers is I think very less in Chennai. I don't know what about your areas. Okay, you are wait for 5 minutes. Yeah, I think they are coming one by one students. Okay, you will wait for 2 to 3 minutes. No, screen. Yes, screen is visible for you or not?
Yes, sir.
Screen is visible. Okay. Okay, I think you wait for 1 or 2 minutes. Only 42 is there. I think Nikhil, your class strength is again reduced. I think 72 now. Yes, I think that Nidarshan who is left. Nidarshan, that fellow I think is left. Yes, I think so only 72 is there this time, I think. Yes. Okay, okay, okay. Okay, you are wait for 1 or 2 minutes, then you will start. Screen is visible for you, no? Yes? Yes, yes, yes. Okay. So today we discussed the basic structure of PN junction. Okay? Just wait for 1 or 2 minutes, then we will start now. Just wait. What about 54? 53 is there.
54 also.
Okay, shall we start now? I think out of 72, now 53 is there. Yeah, 52. I think 52. They are coming one by one. Okay. Okay, ma. Anyway, we will start now. Okay. Yes. Okay, I will start because I think now they are coming one by one. Okay, they will join now, I think. Okay, see. Okay, ma. See, the screen is visible. Yeah. Yes. Confirm. PN.
Yes, sir. Yes, sir.
So today you go to see the basic structure of PN junction, that band diagram of PN junction in thermal equilibrium, and you go to see the forward bias and reverse bias junction. Okay. So both the diode is connected to forward bias and the connections to the reverse bias also. Okay. So these 4 topics we go to discuss here. First, the basic structure of PN junction. Okay. So before we move on to this, okay, I think you know very well about what about P type and N type semiconductor and how you go to get that one. Okay. The pure intrinsic semiconductor doped with the pentavalent or trivalent impurities, definitely you get a N type and P type semiconductor. Is it correct? Yes.
Yes, sir. Yes,
Yes.
sir.
Yes, sir.
Yes. Yes. Okay. Now, I think once they form the PN, for example, the P type, N type materials are formed. So initially, they go to form the junction first. That is the first step. They go to form the PN junction. Okay. So that is a basic building block of the nowadays IC circuits, integrated circuits. See the PN junction, because once you impurities added, so you get charge carriers, electrons and holes. So after getting that electrons and holes, okay, how you go to implement that implantation? So that is given by that PN junction is one of the basic of building blocks of the IC circuits, integrated circuits. I think
Sir,
you know. Yes. Yes.
sir, you didn't talk about ohmic contact and Schottky junction, lecture 9.
Yeah, last week we discussed more. Why?
No, sir. Ohmic contact we didn't learn, I think, sir.
No, that is metal semiconductor junction. That is metal semiconductor. See, last week what you discussed is metal with one semiconductor, N type or P type. So now you
Sir,
say
you
this is
posted the lecture on GCR about that I am talking, sir. Lecture 9.
yes, yes.
Sir, that is not taught now.
That already completed last week. Why?
No, sir. No, sir.
No.
No, sir. Ohmic contact, I don't remember, sir.
Sorry. Okay.
Sir,
Okay.
not taught.
Okay. I say. I think last week we discussed the ohmic contact and Schottky junction. Yeah. Whether you after the continuity equation, whether you discussed or not. No.
No, sir, we did not discuss. Sir, we discussed only till that continuity equation only.
Then
Yes,
okay.
sir. Yes, sir.
Okay. I think maybe I instead of that I go to upload that one. No problem. Okay. Anyway, today I will go to discuss both. Okay. Okay. Okay, first you go to take this one, then you go to take that ohmic and Schottky junction, both. Okay, no problem, no problem. Okay, see, now, okay, come here. So the PN junction is formed. See, for example, once the PN junction is formed, okay, so now you go to take both the charge carriers are very close to each other. Okay, so what happens? So simply according to the different diffusion concept, and there's no doubt initially the diffusion takes place. So that is the n region electrons are more, p region volts are more. Simply they go to cross the junctions. See here, when the p and n regions are brought close to each other or contact, there's no doubt the holes diffuses from p to n, and similarly electron diffuses from n to p. Are you understand this? What I'm telling? Say yes or no.
Yes, sir.
Because p side the holes are more concentration. That's why the carrier according to the carrier density the holes diffuses from p to n, and similarly electrons is more where n type. So that electron diffuses from n to p region. So under the thermal equilibrium condition, so now the both electron and holes are diffuse each other, and they go to attain the one certain level. So that gives rise to the drift current, and there is no net transport of carriers due to different diffusion. They go to get cancel each other. Then due to in the same time, both the charge carriers are diffusers. Okay, the Fermi level also attain the constant level, and the built-in potential is formed. Okay, that is a work function is formed. Work function. See, that means, see here, when both are in the thermal equilibrium, if there is no external voltage, please understand for N type and P type, there is an internal potential is applied, developed. That is built-in potential is applied. So that is VBI. V is nothing but potential. You put BI, built-in potential is produced, and the corresponding work function is that pi j. That is a work function pi, corresponding work function. The difference between N type and P type semiconductor. So once the regions are formed, see once the regions are formed, see here the regions are forming here more. Okay, you say that is a depletion region, and you go to see the diagram how the regions are formed and how the Fermi energy is varied, and all these things I go to show one by one. Okay, see, listen. The first, this is a P-type semiconductor and this is N-type semiconductor. Whether diagram is visible for you or not, more please.
Yes, sir. It's visible.
Visible. Okay. Say in the before merging, where is your Fermi energy of N type? Very close to conduction band. See here, that EFN. And similarly, here this is P region, P side. This is EFP, the Fermi energy of P type. That is very close to valence band. Are you understand this? Say yes or no.
Yes, sir.
See, this is P side and this is your N side. Okay, the Fermi energy is there. So this is for N side, the Fermi energy is very close to your conduction band here, and P side, the Fermi energy is very close to valence band here. And this is before merging or before contact. P and N. After what happened? You go to see when the PN junction is formed. See, once the junction is formed, see here, after merging the N type and P type regions, see here, after merging this. So how that in thermal equilibrium, how that P type and N type semiconductor, that energy levels comes. See here, in the next diagram I go to show. So please carefully listen. Your EF is here, and the EF is also here. This is very close to EC, and this is very close to EP. That is N and P regions. So now you go to see how that energy level is there. See here. So this is the energy band diagram in thermal equilibrium of PN junction diode. PN junction diode. See in the thermal equilibrium. See here. So that this is EC more EC. It is coming and is moving towards EF. After that you get the straight line here. See that now the EF is a straight line here. EF is a straight line. Fermi energy is a straight line. Okay, and for N region that is very close to EC. For P region that is very close to EV. So like that, your energy band diagram is slightly shifted. And the middle one is nothing but the middle one is same. See here the previous diagram, the EI is middle. EI means the Fermi energy of intrinsic carrier. I think almost you know what is EI. E. Yes, I understand what I am telling. Say yes or no.
Yes, sir.
Yes. Okay, that EA is the Fermi level of pure semiconductor, that is intrinsic semiconductor. So that is exactly it is the EA here. See the next diagram, simply there is no change here. This is the dotted lines. The middle see here that is EI, and N region, this is my N side and this is my P side. So N type, P type. That N type, see where is that energy? That EF is very close to EC here. And similarly, what about P side? My P side, that EF is very close to EV. So like that, the diagram is completely changed. That is energy band diagram. This is the energy band diagram of PN junction in thermal equilibrium condition. Are you understand the diagram here now? Or if any doubts or clarifications, please ask. Yes? Anyone more? See, are you understand or not?
Yes, sir.
See, once the PN junction is formed here, once, for example, the junction is formed, okay, so how this, see, that energy level, see here, and this is your built-in potential, see here, that Q pi I is there, so this is pi I, so now the built-in potential is formed, that is already told, and this is the region, that built-in potential region here, and similarly, this is the region for built-in potential. So this is under the equilibrium condition. Under the equilibrium condition, when both the P and N type semiconductors are joined base to base, okay, so now you get the energy band diagram like this. Then what is the equation? That equation already we discussed in the module, same module 2, that lecture 2 and 3, and the same is repeated for P region. See, for P region, my EF is nothing but EIP minus KT log of NE by NI, and for N region, that is EI minus KT log of ND by NI. So what about NA, ND, NI? Anyone? Whether are you remember or not? What about NA, ND and NI? Yes? I think these things already we discussed. What about NA here? That is anyone more? Anyone? What about N suffix A, N suffix D, that NI? See, that is the equations, the Fermi energy equation of N region and P regions. So that is equal to EIP minus KT log of. So what about NA? Anyone? Any students? What about that A and D indicates? Whether I am audible or not? See, I am audible or not here?
Yes.
Yes, sir.
What about that A and D? That's what I'm asking. See, then only you understand, yeah. See, in that equation, so what is the N suffix A here? That is concentration of acceptor atoms. What about n suffix D? Concentration of
Depletion.
Diffusing atoms.
donor,
Deplete.
Donor, yes, sir. Donor.
See, donor, except what about Ni? Ni is nothing but the carrier concentration of
Intrinsic.
intrinsic
Intrinsic.
semiconductor. Ah, yes.
Intrinsic semiconductor.
Yes. So that is the number of electrons or holes in the intrinsic semiconductor. So once the junction is formed, see how the equation goes to change. See here. So that is EIP minus EIN. That is built-in potential. That is VBI. See, the difference is go to take in the VBI built-in potential. That is equal to KT into log of NA by NI square. So that is NA here. The concentration of both donor and acceptor number of donor atoms per unit volume and the number of acceptor atoms per unit volume divided by Ni square. So this is the built-in potential formed when the PN junction is formed, the region is formed. So that region is identified where exactly at the center, in between the P and N regions, the built-in potential is formed, VBA is formed. Are you understand this? Yes or no? Yes? Yes. Okay, next diagram. I think one more diagram I go to show. See here. So in this
So
diagram,
what is BI?
see this is a built-in potential. Built-in potential. See here, V, that is a symbol for potential. BI, built-in potential inside that once the junction is formed, the potential barrier is formed. That is we are identified by VBA. Okay. Yes.
Okay, sir.
Okay. Next to see here. And this region here, conduction band and valence band region for N type and P type. So the here P region excess of holes are there, and N region the excess of electrons are there. Once the region is formed, once the P junction is formed, see how this energy level changes. See here. So this is energy before and this is after. Okay. For N type and P type region, and the P N junction exactly here is the junction is formed. So this middle region you say the depletion region. Here is the depletion region. Understand? Yes. See whether you understand the diagram or not. Say yes or no.
Yes,
Then only move on to the next one. Whether you understand or not. Yes. Next. What? See next to the same PN junction. So connected to forward and reverse bias. So here I don't say anything. I think you only say. So what about forward bias junction means? Say for example the PN junction is forward bias. Okay, what is the meaning? Anyone? Yes. Tell me, Ma, what about the forward bias? I think you studied in the lower classes, yeah?
The positive terminal battery is connected to P region and the negative terminal of battery is connected to N region.
Okay, correct. So when the PN junction is connected to forward bias means whatever you said correct, that the P is connected to positive and that N is connected to negative. Okay. Once that is connected, that is forward voltage is coming. So that the difference is that the VBA minus VF. So when VBF is less than, that is VF is less than VBI. Okay. Simply there is no way to cross the junctions, the charge carriers. And when the applied input voltage increases, that is the forward voltage increases at one stage where that VBI minus VF goes to 0. So when that is goes to 0, VBF is exactly equal to VF, or the applied input voltage is equal to the built-in potential. So that time the depletion region completely vanish. So now the electrons and holes easily cross the junctions. Okay, and this is given in the next diagram. See the potential difference across the depletion regions is identified by that the VBI minus VF, and the width of the region goes on decreasing. More and more input voltage is applied. That the forward voltage is applied at one stage. The VF is far greater than VBI. So definitely there is no depletion region. Now electrons and holes are easily cross the junctions and increase the diffusion current also. So that is the forward biasing condition. You go to see the diagram here. So in the diagram at equilibrium condition, you see before connecting forward bias at equilibrium, So this is the potential VBI, built-in potential is there. So in the below diagram, and the region is identified that VBA. Once the diode is connected to forward bias here, the P is connected to positive and the N is connected to negative here, forward bias is connection. So what about your width of the region now? And VBA VF is reduced. So why that is reduced? Any idea? Yes? See why the width of the region goes on decreasing?
Because the transfer of electrons take place, sir.
Transfer of electrons. Sorry, okay. Anyway, I give one such say the P side, which one is majority? P side, which is majority? Holes or electrons?
Holes.
Holes. What about the N side?
Holes.
N region.
Electrons.
Electrons.
Okay. Now come to one P to positive means the positive is that. What about like charges? Attract or repulse?
Repulse.
Repulse. Similarly, N side electrons that is connected to negative repulse. So the repulsion takes place. What about your built-in potential that depletion region goes on decreasing? Is it correct? Say yes or no.
Yes, sir.
Yes. Yes. So once that VF, that forward voltage is exceeds this VBI, simply here there is no region. So that point only you say that is a knee voltage here. See the graph. So initially there is no current here. See here the potential increases. Simply the current remains zero. I think last practical I explained all these things. Is it correct? See last week practically we did this forward bias characterization. Are you understand? Yes.
Yes, sir.
PN junction diode forward bias characterization already you studied in the last week practical. That's all. Very simple. Okay. So that characterization curve is like this. See here. So initially the input voltage increases slightly. There is no output current. So once that VF is slightly greater than the output current started at one stage where the output current suddenly increases. You see that is a knee voltage or saturation voltage like that. So that you go to mentioned here. And this is the characterization, forward bias characterization and biasing. So what happens when reverse bias? The next one is reverse bias. See, when the same PN junction, so now is connected to reverse bias. So reverse bias means the P is connected to negative now and N is connected to positive now. That's all. Very simple. Okay. The P region is connected to negative and the N region is connected to positive. Okay. See here, and the region automatically change connected to positive terminal. The potential across the depletion region now that VBI plus VF. See last time that is VBI minus VF, the difference. But this time that is added due to this where width of the region goes on increasing. You see the diagram here. And you understand this? You see the diagram? Yes?
Yes, sir.
So this time the region is goes on increasing. What is the meaning of goes on increasing means P is connected to negative means that is holds negative, unlike charges attract. Similarly electrons N side connected to positive attract. So both are attracting. Your region is goes on increasing. That VBI plus VF, that built-in potential, and this reverse voltage goes on increasing, where region width is also increases. Width of the region is also increases, and you see the diagram here. No way to cross the junctions. That N and P side, the electrons and holes no way to cross the junctions now because the region already increased. Width of the region increase. But anyway, in the reverse saturation also, there is some saturation is there. The reverse current is increases and it completely destroy your diode, PN junction diode. Okay. So how you go to avoid such things means that is your Zener diode. So I think you know the name Zener. Whether you identify, remember the name Zener diode? Any idea?
Yes,
Yes.
Yes.
Sir.
Yes. Yeah. What is the major difference between normal diode and a Zener diode?
So
Anyone?
the potential remains constant.
across the
Potential remains constant or see in the Zener diode means there is a voltage regulator. I think you studied voltage regulator. Say okay. So for your refrigerator and most of the electronic devices nowadays you are getting the stabilizer. Why? What is the
Because
reason?
of the fluctuation in the voltage.
So that the fluctuation, that increasing decreasing is regulated by the Zener diode. That is the reason you say Zener diode is acting as a voltage regulator. In the reverse bias also the Zener diode will conduct. But what about our normal diode, ordinary diode? The forward bias, the diode will conduct. The reverse bias, the diode does not conduct. But the reverse current increases suddenly and it damages the diode. The diode completely damaged. So that is a reverse saturation current. Okay, see here. The built-in potential VBA plus VEF goes on increasing in the reverse bias circuits. Simply the diode does not conduct. And the next one more diagram shows the entire characterizations of that both forward bias as well as reverse bias. See here, the forward bias voltage increases, the current slowly increases at one stage where the current suddenly increases means you say that is a knee voltage or a saturation voltage. In the second reverse bias also it is same, but that is a reverse saturation or reverse breakdown voltage here. See, so on the at this stage, definitely your diode completely destroyed. Okay, understand? So yes or no? Yes, or you understand or not?
Yes, sir.
Yes.
Yes,
Yes,
sir.
So this is PN junction. Yeah, that is PN junction, and forward bias and reverse bias. See how first junction formation, PN junction formation. So what happens when the PN junction formation? Okay, the depletion region is formed, or the built-in potential is formed, and you go to study what happens when your PN junction is connected to forward as well as reverse bias. So that is these 12 slides here. That's all. And the corresponding symbol is also given. See, this is the NP, P and N junctions. The corresponding diode symbol is given here. So this is the symbol. So what about here? That triangle is connected. So P side and this vertical bar you say that is the end region like that. You please understand. Anything else more here? Any doubts? Any doubts or anything?
No, sir.
What is knee?
That is saturation voltage. Yeah, that is where your current increased enormously. See here at this stage, suddenly the current increases, the forward current increases. So that point you say that is a knee voltage. Knee voltage. Okay. Yes.
Okay, sir. Okay.
Any other doubts of this? I think this is your last slide in that PN junction. So now in the PN junction, first what you say, how the junction is formed at the thermal equilibrium, how that energy band of this PN junction is there. So definitely the question is coming here. This is very important one. And what happens when the junction is connected to forward bias and reverse bias also. Okay. Yes. So yes or no more. Then only I move on to the next one.
Yes, sir.
Yes. Okay.
Yes, sir.
Okay. Okay. Yeah, okay. Okay. Now I go to share that one more screen. Just wait. See that I think these things already you studied or not? Yeah, that metal semiconductors last week. No. I think I remember I will discuss here these things.
No, sir.
No. Okay. I think whether you go to see the diagram, you remember this one or not? No. Yes.
Yes, sir. This diagram was taught, but
Hmm.
things differ.
Okay. Anyway, I will explain that. No problem. Okay. See, listen. This. So after the PN junction is formed, so this is metal semiconductor junction. See the just now you see what is that the PN junction formation takes place. So how that the PN junction formation is acting as a forward bias, as reverse bias, and etc. etc. Now metal semiconductor junction. What is a metal semiconductor junction? That is now you go to take either N type or P type semiconductor. Then you go to contact one metal here. So due to this, the electrons are able to move from semiconductor to metal or metal to semiconductor. So now we get rectifying and non-rectifying junctions. There are two different junctions you go to take. One is rectifying junction, that is a Schottky junction. The other one is the non-rectifying junction, that is ohmic contact. There are two different metal semiconductor junction formation takes place. See here in the diagram, you go to see the diagram here first. See one side. See, this is a metal is here, and this is semiconductor here. Okay, before connecting, this is before connecting. So what about the work function? The work function of metal is slightly greater than this. See, this is pi m, and this is your pi s. So definitely the pi m is slightly greater than pi s. Is it correct? Say yes or no. Yes.
Yes, sir.
Yes. Yes. So once the junction is formed, you see here. Once the junction is formed, metal semiconductor junction. For example, here the junction is made. So what is the meeting of junction? And the conduction electrons begins to flow from the semiconductor and enter into the metal until the Fermi energy on both sides becomes equal. Therefore, the metal becomes more and more negative now, and the semiconductor becomes more and more positive now. So due to this, the built-in potential is produced, and the work function is formed, that is pi m minus pi s equal to EV. So this potential is applied where to the system after contact. You go to see the here, and due to the electrons coming from the metal semiconductor to metal side, where Fermi energy level slightly increases, you say you get the curve, upward curve like this. See, the height of the barrier on the semiconductor side increases by this Vs plus P, and the metal remains unchanged. Therefore, the junction is said to be the forward bias. In the reverse bias condition, and the same, and the current will flow from metal to semiconductor here. Okay, see, okay, and from the diagram, you go to see the diagram here. Simply, this is a upward curve like this is there. See here, this is before contact, and this is after contact. This is pi m, this is pi s. So initially pi m is greater than pi s. So after that, the built-in potential formed here. See, the pi m minus pi s, that is equal to EV formed here. That's all. So this is metal semiconductor junction, that is rectifying junction here, this one. So in the forward bias, similar to your PN junction diode, that metal semiconductor junction is conduct. The reverse bias, same, that is not conduct. That is the reason you say that is a Schottky junction. Schottky, that is a rectifying circuit. Are you understand? Say yes or no.
Yes,
Yes?
sir.
Okay. See, the next diagram, I think again you go to see here. So once the junctions are formed, see, so why that upward curve is taking place? That's why I'm telling. See, slightly the Fermi level increases and shifted towards your see here. Okay, and that EF is there. So simply that is your increasing height is slightly increases like this. So that is the reason you get the curve is like upward like this. So for this metal semiconductor junction, especially for your Schottky junction. But ohmic contact, that is downward direction. That is downward direction. That is for ohmic contact. Okay. Yes. See, I understand this concept or not? Schottky junction.
Yes, sir.
Okay. Next, come to the ohmic contact. Next, see the diagram characterization. You go to see the characterization. Already told. Forward bias similar to our PN junction diode. The reverse bias, nothing is happened. See here, that is IV characterization of Schottky junction. The forward bias is similar to your PN junction diode is conduct. Simply reverse bias, nothing is there. It remains constant. See, your the current remains constant here. Whatever there is a change in voltage, the current remains constant. Simply does not conduct. That is the reason you say this is a rectifying circuit, rectifying junction, Schottky junction. Yes. Say yes or no. See whether are you understand or not.
Yes, sir.
No, others nothing is there. Yeah, only one or two sounds are. What about others?
Yes, sir.
They are in the class or not? I don't know. Yes.
Yes, sir.
Yes. Okay, then come to your next ohmic contact. Ohmic contact here also same. and that the work function is here, and then pi s is slightly greater than pi m. See the lead that pi m will be the work function of metal and semiconductor. So here pi s is slightly greater than pi m. So last time pi m is greater than pi s. This time pi m is less than pi s, and the ohmic contact is same. Once the metal is connected to either n type or p type, now the electrons are coming from metal to semiconductor here. See here that electrons are beginning to flow from the metal to semiconductor until the Fermi level lies on both sides of junction becomes equal. And due to this, the metal gets more and more positive, and the semiconductor gets more and more negative here. And the corresponding the resting potential or the resultant potential is given by that pi s minus pi m, that is equal to EV. So the potential is applied. So simply the system here to the after contact such that the n type is connected to positive and the metal is connected to negative charge. The electrons will flow from semiconductor to metal without encountering any appreciable barrier here. The reverse bias also same condition here. That is the reason you say there is a non-rectifying circuit. Similarly, the voltage is reversed. See here, when the semiconductor is connected to negative and metal is connected to positive, again the electrons will flow from metal to semi without any change in the barrier. So both the cases, the current is directly proportional to your applied voltage. So that is your Ohm's law. So that is the reason you say this is ohmic contact. Ohmic contact, both the forward as well as your reverse conditions. So here that the current is directly proportional to voltage. Understand? Say yes or no. Yes. So the diagram we go to see here. Say before contact, this is pi m metal and that is semiconductor. So here the pi s is greater than pi m. That is the initial condition. So once the junction is formed, see here the electrons are moving from metal to semiconductor here initially. Okay, that's why you see that is upward curve like this. See here the upward curve like this. Both the forward and reverse bias it will conduct. So that is the reason you say this is non-rectifying circuit, non-rectifier or non-rectifying junction. That is your ohmic junction. And this is a corresponding diagram here, before and after contact, how that the built-in potentials are formed and etc. etc. See here. Okay. Any, see the diagram is visible for you? Yes?
Yes, sir.
Yes. So this is your ohmic contact. Okay. See here how that variation takes place in the ohmic junctions. I think that is. Are you understand this both? Are you understand or not?
Yes, sir.
Yes, sir.
Yes, I think so. This is a short key. Short key means rectifying, and the ohmic means non-rectifying. Say in the I think in the ohmic characterization that characterization diagram is missing, but anyway that is a straight line here. That's all very simple. Both the forward and reverse bias condition, you get the straight line because the voltage, the current is directly proportional to voltage, so you get the straight line. That's all. So that is your ohmic junction, ohmic junction, or ohmic contact. Anything else? By any doubts here? Any doubts here now? Say yes or no. Anything else or any doubts? Yes? Say any doubts?
No, sir.
This ohmic junctions, Schottky imperfections is the PN junction diode. I think today go to take some important PN junction diode formation. What happens that the forward and reverse bias again? How the metal semiconductor junction is working, both forward and reverse bias. So why you say this is rectifying and non-rectifying circuits like that? Schottky junction and ohmic contact like that. Okay. Yes. Anything else or any doubts? Please you go to ask. Any clarifications here? Say yes or no more. Any clarifications or any doubts? No, okay, okay. Then I go to stop the share screen. Just wait. Okay, so now come here. See, what about the Nikhil? See, this week, yes. So this week, all of you go to submit your assignments, theory assignments. Last week, okay. So I think you asked to extend the date. I already extended. So please, all of you go to submit your theory assignment end of this week itself. Okay. Yes. The practical, okay. Practical already you submitted. I received someone. Okay. But anyway, that is a routine work. Then leave it. Theory, please, you go to submit this end of this week. Assignment, theory assignments. Okay. What about attendance? Just wait. I will take the attendance. I think 66 is there, yeah, out of 72. Just wait. See, your section, the strength is goes on decreasing. I don't know why, what happened. Huh? See, they are shifted to another college or yes? Oh, like that. Okay, okay, okay. Okay, what about 51? Atul Gupta. Say, Atul Gupta is not there. 52? 53? Okay, give your attendance. Say, all of you. Please, all of you give your attendance. 53? It's not there. 54?
Present, sir.
55? 55? It's not there. 56 is also not there. 57?
Present, sir.
58?
Sir, yes,
58
written.
is present, sir.
Okay, chat box. 59?
Hmm.
60?
Present, sir.
61?
Present, sir.
62?
Present, sir.
63?
Present, sir.
64? I think 64 is left, I think. Nikhil? Yes, you confirm. I think 64 is left, that fellow, Nidarshan. 65? I think 65 is also long absent. 53, what about 53 is present? Mic not working. Okay. 66?
Present, sir.
68?
Present, sir.
69?
Present, sir.
70?
Present, sir.
71?
Present, sir.
72?
Present, sir.
73?
Present, sir.
74?
Present, sir.
75?
Present, sir.
76?
Present, sir.
Hey, 76. Are you submitted experiment number 1 or not? Assignment 1 experiment. 76.
No, sir. At the time I was doing.
Huh? No, I can't. I can't understand. What 76? Which number 76? 76. That fellow is okay. 77.
Present, sir.
28. 29.
Present, sir.
80.
Present, sir.
81.
Present, sir.
83. 83.
Sir, 81 present.
81%. Okay. What about 83? Okay, it's not there. Fourth floor. 84.
Present, sir.
85.